2.5 million years. That is the time it would take light, the fastest thing the universe permits, to travel from here to the nearest galaxy. Light, traveling at roughly 300,000 kilometers every single second. 2.5 million years. The Milky Way would live and die several times over before a single photon sent today arrived at its destination. And light isn't even a spacecraft. It doesn't need fuel. It doesn't slow down. It has no mass to drag it back. It just goes. At the absolute ceiling speed of reality. For 2.5 million years. Straight. That single number has collapsed more science fiction dreams than any government budget cut in history. And here is what makes that number truly brutal. Andromeda is the closest galaxy we could point at. There are 2 trillion others beyond it. Some of them sit so far away that the light they sent before our sun was born hasn't reached us yet. The universe, it turns out, is not a place we were designed to explore. It is a place we were designed to observe from a fixed position, like an insect trapped in amber, looking out through the glass. If that idea unsettles you, good. It should. Because what we're going to do in the next hour or so is actually sit with that discomfort and understand exactly why it exists. Not in the vague, hand-waving way where someone just says, space is very big. We're going to trace it down to the physics, the mathematics, the documented history of how humanity discovered its own confinement, and why even the most creative engineering minds of our era, armed with every theoretical propulsion system ever imagined, run straight into the same wall. And if this kind of question keeps you up at night, the way it keeps me up at night, subscribe and hit the notification bell, because we are just getting started. And what comes next is considerably stranger than the number you just heard. A century ago, the word universe was simply a synonym for the Milky Way. That was not ignorance. That was the honest conclusion of the best telescopes and the sharpest minds available at the time. The fuzzy, smeared patches of light that astronomers had been cataloguing for over 100 years, the ones that glowed faintly between the stars and never resolved into anything clean or sharp. Most people assumed they were nearby gas clouds, part of our galaxy, ours, an internal phenomenon, like fog in a forest. In the early 1900s, astronomers were divided over whether the faint, unresolved smudges seen glowing in the night sky were relatively small gas clouds lying on the outskirts of the Milky Way, or enormous island universes, galaxies just like our own. The idea of island universes, whole separate cities of stars separated from us by unimaginable void, had been floating around since the 18th century, when philosophers and early astronomers started entertaining the thought that what they were seeing through their lenses might not be clouds at all. But no one had any hard evidence either way. It was informed speculation against informed speculation. By 1920, the argument had reached fever pitch. The idea for a formal debate was sown in 1919, when George Hale, head of Mount Wilson Observatory, proposed a structured public discussion at the National Academy of Sciences to thrash out the merits of the island universe theory. The Academy secretary was initially skeptical, worrying the debate would fall flat because the audience wouldn't care about island universes. He was wrong. On the evening of April 26, 1920, the debate was held at the Smithsonian Institution in Washington, D.C. 2 astronomers took opposite sides. Heber Curtis, 48 years old, argued on behalf of island universes, and Harlow Shapley, 34, essentially on his own behalf. At 8:15 sharp on that Tuesday evening, the 2 men faced an audience of academics, members of the public, and, so the story goes, Albert Einstein. Shapley's position was actually the more audacious one in a certain sense. He argued that the Milky Way was everything, vast, enormous, the entire cosmos. He came down on the side that said the Milky Way was everything there was, and that the spiral nebulae were strangely shaped clouds within, or perhaps just outside, its bounds. The data he had assembled from globular clusters, mapped painstakingly across the sky, suggested the galaxy was so enormous that there was simply no room, conceptually or geometrically, for anything else to compete with it. The universe was ours. We were near its edge, not its center, but it was still ours. Curtis disagreed completely. Following in the footsteps of the 18th century German philosopher Immanuel Kant, Curtis believed that many nebulae were island universes, extremely remote collections of billions of stars, comparable to our home galaxy. He pointed to the fact that some of those fuzzy smears showed what looked like internal structure, spiral arms, lanes of dust, patterns that looked nothing like gas, and everything like a rotating disk of stars seen from an angle. The evening ended without a clear winner. Both men were partly right and partly wrong. Curtis correctly assumed that spiral nebulae were individual galaxies, but Shapley was right about the extended three-dimensional distribution of globular clusters and the off-center position of our Sun in the Milky Way. As noted astronomy historian Virginia Trimble once said, Shapley and Curtis each had hold of portions of the correct elephant. But the elephant itself would not be confirmed until 3 years later, in an observatory on a mountain in California, by a man with a photographic plate and a pencil. Edwin Hubble was not looking for revolution. He was doing what astronomers do, taking long exposures of faint objects and cataloging what he found. Using the 100-inch Hooker telescope at Mount Wilson, then the largest telescope in the world, Hubble identified Cepheid variable stars in the Andromeda galaxy. Cepheid variables are stars that pulse. They brighten and dim in a regular, predictable rhythm, like a cosmic lighthouse. And crucially, their pulse rate is directly tied to their true luminosity. That connection had been discovered a decade earlier, not at a grand telescope by a celebrated astronomer, but by a woman sitting at a table inside the Harvard College Observatory, staring at photographic plates, hour after hour, year after year. Henrietta Leavitt worked at Harvard College Observatory as a human computer, tasked with measuring photographic plates to catalog the positions and brightness of stars. Women computers at the observatory were considered too frail to operate the telescopes at night in the cold temperatures. Their job was to sit indoors and measure. Leavitt measured with extraordinary precision. In 1912, she published her findings showing that Cepheid variable stars have a simple relation between the brightness of the variables and their periods. A discovery she well understood could be applied to the problem of measuring the distance to celestial objects too far away to be measured by parallax. These variables became the first known standard candles for measuring extragalactic distances and remain the gold standard for this task today. Hubble would pick up her ruler 11 years later and use it to dismantle everything Shapley had argued. Leavitt died in 1921. She never found out what her work proved. Hubble used it, painstakingly taking images every clear night, hunting through the Andromeda smear for a star that blinked on a regular schedule. By examining one star's light curve, Hubble correctly surmised that he had discovered the first Cepheid variable in M31, and he crossed out the N for nova on his photographic plate and replaced it with VAR. When he combined his observations with Leavitt's period luminosity law, Hubble concluded the star's distance was far greater than even the upper limits of the Milky Way's diameter at the time. His initial estimate was significantly lower than the true figure. He didn't yet know there were two distinct types of Cepheid variables, each with different intrinsic luminosities, which caused him to underestimate the scale. We now know the true distance is 2.5 million light-years. But even Hubble's underestimate was enough to settle the question permanently. Andromeda was not a cloud inside our galaxy. It was another galaxy entirely. He wrote to Shapley. Shapley was devastated. He lamented to fellow astronomer Cecilia Payne-Gaposchkin, who was in his office when he opened the letter. "Here is the letter that destroyed my universe." It is one of the most honest sentences in the history of science. Because Shapley was right, in a real sense, a universe had been destroyed. The comfortable, comprehensible, single galaxy cosmos that humans had lived inside conceptually for millennia was gone. The conclusion was as amazing as it was revolutionary. We live in a vast universe, our Milky Way being one among billions of other galaxies spread across the empty vastness of space. Our place in the universe suddenly became very mundane indeed. That mundaneness is worth sitting with, because it's not just that the universe got bigger, it's that the things that got added to the map were forever out of reach. When the universe was one galaxy, everything in it was at least theoretically visitable. Once it became 2 trillion galaxies scattered across incomprehensible distances, the map became a prison sentence. Let's make sure you understand exactly what a galaxy is, because the word gets thrown around until it loses weight. Forget the abstract for a moment and come with me on a scale comparison. The Milky Way is estimated to contain between 100 and 400 billion stars. 400 billion. If you tried to count them at 1 per second, you would need 12,000 years. That's longer than all of recorded human civilization. And that's just the counting. You haven't moved anywhere yet. Those stars form a large disk whose diameter is about 100,000 light-years. Light, the fastest thing that exists, takes 100,000 years to cross our own galaxy from edge to edge. Walking across it at a brisk pace would take roughly 2 billion years, assuming you could somehow walk through open space and didn't need to sleep or eat. The number is so large, it functionally loses meaning unless you find a comparison that brings it back to Earth. So try this. If you reduced the entire solar system, the Sun, all 8 planets, all the way out to the orbit of Neptune, to the size of a small coin, a 10-pence piece, something you could hold between your fingers, then the Milky Way at the same scale would be roughly the size of continental Europe. That coin, lost somewhere in the middle of France, 2/3 of the way from the western edge, that's us. The solar system is located within the disk, around 2/3 of the way out from the galactic center, on the inner edge of a spiral-shaped concentration of gas and dust called the Orion's Cygnus Arm. If the center of the Milky Way were a city, we would be living in suburbia, about 25,000 to 30,000 light-years from the city center. Not a dramatic suburb, an ordinary one. No particular distinction. The kind of neighborhood where nothing especially important happens, and the commute to the center would take 25,000 years, even if you could somehow travel at the speed of light. This galaxy is so enormously large that our solar system takes about 225 to 250 million years to complete a single revolution around its center. In astronomy, this is called a galactic year. 1 galactic year ago, dinosaurs on Earth were just emerging, and mammals were yet to evolve. We have completed roughly 20 orbits since the Sun was born. 20. In a galaxy that appears by all evidence to have been spinning for over 10 billion years. And we haven't left yet. We haven't even meaningfully moved within our own galaxy. But here is where it gets genuinely disorienting. That galaxy, vast, ancient, with its 100,000 light-year diameter and its hundreds of billions of stars, is not alone. The Milky Way has several satellite galaxies, and is part of the local group of galaxies, forming part of the Virgo supercluster, which is itself a component of the Laniakea supercluster. Our nearest major neighbour, the one that Hubble's pencil marked VAR on that autumn night in 1923, sits at a distance that simply refuses to translate into human intuition. Andromeda, 2.5 million light-years away. Think about what that means concretely. Hubble found a star in Andromeda that brightened and faded in a predictable pattern, like a lighthouse beacon. The light from that star, when it finally reached Hubble's photographic plate, had been traveling continuously since before our species existed, since before the first Homo sapiens looked up at a night sky, since before our ancestors were recognizably human. That ancient light completed its journey, hit a glass lens on a California mountaintop, and told us, there is another galaxy, and it is over there, and you will never go there. The fastest spacecraft humans have ever built is the Parker Solar Probe. At its closest approach to the Sun in 2024, the probe reached a speed of 690,000 kilometers per hour, 0.064% of the speed of light. It is the fastest object ever built on Earth, the fastest object ever made by humans, and it is moving at 0.05% of the speed of light. At that speed, the journey to Andromeda would take $4,000, and I want you to feel the full weight of this number. Roughly 4 billion years. Longer than the Earth has existed. The Sun would have burned out and gone cold before the probe arrived. But forget the probe. Let's say we somehow cracked the engineering problem. Let's say we built something, hypothetically, that could sustain 10% of the speed of light. Something that does not exist and that we have no current physics to build, but let's grant it. 10% of light speed. At that speed, the journey to Andromeda would take 25 million years. Roughly 1 million generations of human beings would need to live and die on the ship before it arrived. Your civilization would need to survive, intact, through a time span longer than the gap separating us from our earliest primate ancestors. The mission briefing would need to survive longer than the entire history of complex multicellular life on this planet. The numbers keep being this way. No matter what speed you plug in, 5%, 20%, 50%, the distance simply overwhelms it. Andromeda is not just far, it is categorically, architecturally far. It belongs to a different scale of reality than any distance humans have physically related to. And yet, here is where the physics becomes genuinely interesting. There is a loophole. Sort of. A strange, subtle, unsettling loophole, written into the equations of special relativity. Einstein's equations say something counterintuitive. As you approach the speed of light, time for you slows down relative to the universe around you. At 1g, a human comfortable acceleration, you could, in principle, reach the Andromeda galaxy in about 28 years of ship time, while 2.5 million years pass on Earth. 28 years. One human lifetime. Technically survivable. Technically a mission that could be described in a briefing document as something a person might actually experience. The catch, and it is a catastrophic catch, is that the 28 years is only true from inside the ship. Back on Earth, 2.5 million years would elapse. Every person you knew, everyone your civilization ever produced, every monument ever built, every language ever spoken, every idea ever recorded. Gone. Twice over. By the time you arrived at Andromeda, and your signal announcing, "We made it," began its return journey, there would be nobody left who sent you. Nobody left who even remembers a species called human sent a ship anywhere. That is what time dilation actually means in practice. It is not a technological shortcut to the stars. It is a one-way door that severs you permanently from everything you came from. You arrive, but you arrive alone, in a universe that has moved on 2.5 million years without you. And we haven't even talked about the energy yet. The required kinetic energy diverges to infinity as velocity approaches the speed of light. Special relativity makes acceleration impossible beyond that ceiling for any object with mass. Think about what that means physically. As you push a spacecraft faster, it doesn't just get harder to accelerate, it gets increasingly harder in a way that never levels off. The moment something starts moving at a significant fraction of the speed of light, both its energy and its resistance to further acceleration grow far beyond what classical physics predicts. It is like trying to push a shopping cart that gets heavier the faster it goes, until adding more force barely moves it at all. And then the fuel requirement appears. And this is where the engineering argument doesn't just get difficult, it gets genuinely absurd. Accelerating to the Andromeda galaxy with constant acceleration and deceleration requires roughly 42 trillion kilograms of fuel for every single kilogram of payload, assuming a completely perfect, 100% efficient engine that converts matter directly into energy. That is 10 times the mass of Mount Everest needed in fuel for every kilogram you want to arrive. 10 times the mass of Mount Everest per kilogram of payload, not per person, per kilogram. A single human being, at roughly 70 kilograms, would require a fuel mass approaching 700 times the mass of Everest. The ship carrying that person would require proportionally more. The fuel to carry the fuel would require even more. The numbers don't converge. They spiral upward into a regime that no physical object in the observable universe could provide. The next best option to matter-antimatter annihilation, which would be 100% efficient at converting matter into energy, is nuclear fusion, as it works in the Sun. And that only converts 0.7% of its initial rest mass into usable energy. Everything we actually know how to do in practice, chemical rockets, nuclear fission, ion drives, falls orders of magnitude short even of the antimatter baseline, which is itself so far beyond our current capability as to be science fiction. I'll be honest. When I first worked through these numbers, I assumed I'd made an error somewhere. The fuel ratio is so extreme, it felt like a mistake. It isn't. It's the rocket equation meeting special relativity, and the combination is pitiless. You cannot engineer around this. You cannot wait for a breakthrough that makes the numbers manageable. The numbers are what they are because of the shape of space-time, not because we haven't been clever enough yet. The speed of light is not a speed limit in the sense of a highway sign that someone could lobby to change. It is a feature of the universe's geometry. Space and time are woven together in a way that makes the ceiling absolute. No body can be accelerated to the speed of light, because the acceleration of a body decreases to zero as its speed approaches light speed, however large the accelerating force applied. You can push harder. You can push forever. The gap closes asymptotically and never reaches zero. The wall is real. It is physical. And Andromeda sits on the other side of it. There is, though, one more dimension to this problem that rarely gets the attention it deserves. And it is the dimension that transforms very difficult into literally impossible for the vast majority of the universe. The galaxies beyond our local group are not just far away. They are leaving, right now, continuously. The space between them and us is not static. It is stretching. And the further away a galaxy sits, the faster the stretch carries it. This is the discovery that won the Nobel Prize in Physics in 2011, and it came from data collected in 1998 from teams studying distant supernovae. But that story belongs in the next chapter of this journey, because once you understand what those 1998 observations revealed, the word impossible acquires a dimension that even Einstein did not fully anticipate. The year was 1998, and two teams of astronomers were doing something that sounded almost boring: measuring how fast the universe was slowing down. That was the assumption built into every cosmological model at the time. The universe had been expanding since the Big Bang. Everyone agreed on that. The open question was how quickly gravity was putting the brakes on. Measure the deceleration precisely, and you could calculate the ultimate fate of the cosmos. Would it keep expanding forever, or would gravity eventually win, pulling everything back toward a final collapse? The Big Crunch. The answer was going to be a number, a rate, a tidy entry in a data table. Saul Perlmutter had been working on the problem since 1988 at Lawrence Berkeley National Laboratory. His team, the Supernova Cosmology Project, was hunting for Type 1a supernovae, a specific category of stellar explosion so consistent in their peak brightness that astronomers use them the way surveyors use laser levels, as reliable standard candles scattered across the universe. Compare how bright they appear with how bright they should be. Measure the shift in their light toward the red end of the spectrum, and you can calculate both their distance and how fast the universe was expanding when they exploded. The other team, the High Z Supernova Search Team, led by Brian Schmidt, with Adam Rees doing much of the critical analysis, was doing almost identical work. Two independent groups, different instruments, competing for the same answer. Neither team expected a surprise. They were measuring a known phenomenon with better tools, a refinement project, the kind of careful, methodical calibration work that fills out the decimal places. What they found instead was that the distant supernovae were dimmer than they should have been. Not brighter, dimmer. Meaning they were further away than any decelerating universe could account for. The universe was not slowing down, it was speeding up. Something was pushing galaxies apart with increasing force, and that something had no name, no explanation, and no place in the existing equations of physics. Rees was the first to see the signal in the data in late 1997, and his initial reaction was to assume he had made an error. He spent weeks checking for systematic problems, dust extinction, calibration errors, something in the photometry pipeline that might explain away the anomaly. When he couldn't find the error, he brought it to Schmidt. Schmidt, by his own account in subsequent interviews, felt deeply uneasy. Not excited, uneasy. Because the result was not just unexpected, it contradicted the foundations of modern cosmology in a way that felt less like a discovery and more like something breaking. Perlmutter's team was finding the same thing independently. By early 1998, both teams had run out of reasons to disbelieve their own data, and the results went public within weeks of each other. Science journalist Dennis Overby, covering the announcement for the New York Times, later described the atmosphere in the astronomical community as something like controlled panic, a theoretical emergency. The phrase stuck. They called the unknown force dark energy, not because anyone understood what it was, but because they needed something to call it. Dark energy is thought to account for roughly 68% of the total energy in the universe, making it the dominant substance in existence, and we still have no mechanistic explanation for what it actually is. It appears in the equations as a cosmological constant, a term Einstein himself introduced, then abandoned, then was shown by observations to have been right about for entirely wrong reasons. The layer of irony there is deep enough to swim in. But the astrophysical consequence of dark energy is not just philosophically interesting. It is practically devastating for any conversation about intergalactic travel. The expansion of the universe is not new, but before 1998, astronomers believed it was decelerating. Now we know the opposite is true. Distant galaxies are accelerating away from us. And because space itself is expanding, not galaxies merely flying through pre-existing space, but the fabric of space-time actually stretching, galaxies far enough away are already receding faster than light. Not violating relativity. Relativity describes how objects move through space, not how space itself expands. Space has no such speed limit. It can stretch as fast as physics demands, carrying anything riding it along at speeds that make the constraint on matter irrelevant. That distinction matters enormously. It means that the effective boundary of what we can ever reach is not just defined by how fast we can travel. It is defined by how fast the universe is pulling things away from us. And that rate is increasing. Picture a bubble. You are at the center, and the bubble's surface represents the farthest point from which any light sent today could ever reach you. Ever, in the infinite future, even assuming the universe continues to exist. This is called the Hubble volume, or, more precisely, the cosmic event horizon. And it sits at a current proper distance of roughly 16 billion light-years from us. Every galaxy outside that boundary is, right now, receding from us faster than light. Any signal they send, any radio wave, any photon, any particle, moving at any speed up to the speed of light, will never close the gap. The space between us and them is growing faster than any signal can cross it. Those signals start their journey, move forward at the speed of light, and still fall further behind their destination with every second that passes. This is not a temporary situation. It is permanent, and it gets worse. As dark energy continues to drive the expansion, and the expansion continues to accelerate, the cosmic event horizon effectively shrinks in terms of the number of galaxies it contains. Galaxies that are today just barely inside our reachable universe, in the sense that light sent now could eventually reach them, will, over the next few 100 billion years, cross that horizon and vanish from our reachable universe entirely. They do not explode. They do not disappear in any dramatic sense. They simply recede until the redshift of their light stretches to infinity and they fade from any possible detection. They pass through an invisible membrane and they are gone forever. Astronomers have been able to calculate how many galaxies have already passed beyond our observable horizon due to this process. The number is not small. The observable universe currently contains an estimated 2 trillion galaxies. Of those, only a small fraction, in the tens of thousands, concentrated in our local gravitational neighborhood, are actually reachable by any physical object or signal. The rest are already gone, whether we have noticed yet or not. Sit with that for a moment. 2 trillion galaxies, tens of thousands reachable. That is a reach percentage so small it barely registers as a fraction. And the horizon is not static, it is closing. With every billion years that passes, more galaxies cross the line. What is reachable now will be unreachable later. Our grandchildren's universe, on a cosmological timescale, will be a lonelier, more isolated place than ours. The universe is quarantining itself, galaxy cluster by galaxy cluster, behind a wall of accelerating expansion that no engine will ever pierce. There is something almost deliberately cruel about the timing. We live in a cosmological moment early enough to still be able to see the distant universe, to observe billions of galaxies, to study their light, to reconstruct their history. But we will never touch any of it. Future civilizations, if they exist billions of years from now, will look out at a sky with only their own local group visible. They will have no evidence that the rest of the universe exists at all, because no evidence will be able to reach them. They will have to take it on cosmological faith or reconstruct it from ancient data archives, assuming those survive. We are, at this moment in cosmic history, living through the best view the universe will ever offer to any observer in our corner of space-time. And we cannot go anywhere. Except, and this is important, not quite nowhere. Gravity is the one force in the universe that doesn't care about expansion, not at close enough ranges. When two masses are gravitationally bound to each other, when their mutual attraction exceeds the rate at which dark energy is trying to pull them apart, they stay together. They are exempt from the larger motion of the universe, the way a boat tied to a dock doesn't drift away with the current. The local group, the collection of around 80 or so gravitationally bound galaxies that includes the Milky Way, represents our permanent address in the cosmos. These are the galaxies that cannot be taken from us by expansion because gravity has already claimed them. The Andromeda galaxy is not receding from us, it is approaching. Barreling toward us at roughly 110 kilometers per second, pulled by the gravitational attraction between two enormous masses that have been reaching for each other for billions of years. In roughly 4 to 5 billion years, which admittedly is not a timescale for trip planning, Andromeda and the Milky Way will collide. Not in the explosive collision catastrophe sense, because galaxies are mostly empty space and individual stars rarely strike each other directly, but in the slower, more majestic sense of two enormous disk galaxies interpenetrating, distorting, and, over the course of a billion years, merging into a single, large elliptical galaxy that astronomers have already pre-named Milkomeda. The Large and Small Magellanic Clouds, irregular dwarf galaxies visible to the naked eye from the southern hemisphere, orbit the Milky Way and are being slowly consumed by it, their outer stars already being pulled away by tidal forces into streams that arc across the sky. The Triangulum Galaxy, Messier 33, at about 2.7 million light-years away, is the third largest member of the local group. A scattered population of smaller dwarf galaxies, the Sagittarius Dwarf, the Canis Major Dwarf, the Sculptor Galaxy, fill out what is essentially a gravitational community, all held together by their mutual mass. These are the only destinations in the universe that are genuinely, permanently, physically reachable for any civilization based here. Simply because of where we were born, inside a group of galaxies that happened to find each other before dark energy could carry them apart. Everything outside the local group is already gone, cosmologically speaking, receding, accelerating, beyond the horizon or approaching it rapidly. We do not have access to the rest of the universe. We have access to our neighborhood, a small cluster of galaxies huddled together against the cold expansion of everything beyond. And that is all we will ever have. That changes the question somewhat. Not, can humanity reach the nearest galaxy? Because Andromeda will one day come to us. But, can we reach a galaxy we have to travel to? And here the engineers finally get to have their say. Because if anyone could solve a problem like this, it would be the people who spent their careers designing actual spacecraft to actually travel between actual stars. The longest serious engineering study of an interstellar spacecraft was a project called Daedalus. Between 1973 and 1978, a team of engineers from the British Interplanetary Society spent 5 years working out the physics and engineering of a robotic probe that could travel to Barnard's star, about 6 light-years away, within a human lifetime. Not to Andromeda, not to another galaxy, to the second nearest star system to Earth, 6 light-years away, to arrive there within 50 years of launch. The result was a 2-stage vehicle that would have a launch mass of 54,000 tons, of which the overwhelming majority was fuel. specifically pellets of deuterium and helium-3, to be detonated behind a pusher plate at 250 pulses per second. The design achieved a projected cruise velocity of about 12% of the speed of light. Remarkable, genuinely remarkable. And at that speed, it would reach Barnard's star in approximately 40 years of flight time. No deceleration was included in the original design. The probe would fly through the Barnard star system at 12% of the speed of light and have perhaps a few hours in which to observe and transmit data before it was gone. Daedalus was never built. The helium-3 fuel alone doesn't exist in sufficient quantities on Earth. It would need to be harvested from the atmosphere of a gas giant. The engineering challenges of detonating a nuclear pulse 250 times per second inside a vehicle that needs to hold together are extraordinary. And after 50 years of work and technological development, the study remains exactly what it was: a serious, credible demonstration that interstellar travel to a nearby star is theoretically possible, phenomenally expensive, and not achievable with any technology we currently possess. Scale that to Andromeda. At 12% of the speed of light, Daedalus's maximum, the journey to our nearest galaxy would take more than 20 million years. The probe Barnard's Star mission required 54,000 tons of specialized fuel for 6 light years. For Andromeda, at 2.5 million light years, the fuel requirements become a number that has no physical referent in the real universe. There isn't enough hydrogen in the Milky Way to build the fuel tank. The Breakthrough Starshot initiative, launched by Yuri Milner in 2016, takes a different approach. Instead of propelling a large spacecraft with onboard fuel, Starshot proposes accelerating tiny gram-scale light sail probes, barely larger than a postage stamp, using an array of ground-based lasers delivering 100 gigawatts of combined power. The target is Alpha Centauri, 4.2 light-years away. At 20% of the speed of light, such a probe would arrive in about 20 years. It is an elegant idea, and the physics is not obviously wrong. The engineering challenges are staggering. Maintaining beam focus over 4 light years, surviving interstellar dust impacts at relativistic speeds, communicating results back to Earth. But they are not theoretically impossible challenges. For Alpha Centauri, for Andromeda, Starshot runs into a different problem. At 20% of the speed of light, the journey takes 12.5 million years. The laser array would need to sustain its beam across distances so large that maintaining focus becomes geometrically impossible with any plausible equipment. The probe, crossing 2.5 million light-years, would encounter dust, gas, and cosmic rays over a timescale longer than many extinction-level events on Earth. Even if it survived intact, the signal announcing its arrival would take another 2.5 million years to return, and there would be nobody on Earth to receive it. Project Orion, the nuclear pulse propulsion concept from the late 1950s, which proposed a spacecraft that would ride the shockwaves of nuclear bomb explosions detonated behind a massive pusher plate, could theoretically achieve higher payload fractions and greater final velocities than chemical rockets, but still falls catastrophically short of intergalactic requirements. Freeman Dyson, one of the most rigorous and imaginative physicists of the 20th century, was one of its early advocates and spent years exploring its upper limits. Dyson believed Orion-class vehicles could reach perhaps 0.1% of the speed of light with practical bomb masses. At that speed, Andromeda is 750 billion years away, roughly 50 times the current age of the universe. 50 times the age of the universe. The Sun will have died. The Milky Way will have consumed all of its star-forming gas. Black holes will have begun to slowly evaporate through Hawking radiation. And the Orion ship will still have the overwhelming majority of its journey ahead of it. These are not engineering problems. They are mathematical statements about the relationship between distances and energies in a universe governed by general relativity and dark energy. The engineers have done everything right. The universe simply does not cooperate. But suppose some civilization, somewhere in the deep future, cracked the energy problem. Suppose they found a physics we have not found, built an engine we cannot conceive, and somehow launched a ship toward Andromeda. Let us grant all of that as a thought experiment and ask the question the physics students always skip. What about the people? A generation ship is a concept that appears in science fiction and occasionally in serious speculative engineering. A spacecraft large enough to contain a self-sustaining population, traveling for so many generations that the people who arrive have no living memory of Earth and are the distant descendants, hundreds, thousands, tens of thousands of generations removed from the people who departed. For an interstellar mission to a nearby star, say Alpha Centauri at 4 light-years, a generation ship traveling at a modest fraction of the speed of light would need to house and sustain a population for perhaps hundreds of years. Challenging, sociologically complex, biologically demanding, but within the range of things that living systems have survived before. Populations have been isolated for hundreds of years. Ecosystems have been maintained in enclosed environments for shorter periods. The problems are hard, but they are problems of scale, not of fundamental biological impossibility. For a journey to Andromeda, the nearest galaxy, under 2.5 million light-years, our closest extragalactic neighbour, even at 10% of the speed of light, the journey takes 25 million years. At 1% of the speed of light, 250 million years. At any speed that existing or near-future propulsion could sustain, we are talking about geological timescales. 25 million years is roughly the gap between us and the common ancestor of humans and old-world monkeys. It is the span in which a genus can emerge, diversify into thousands of species, and vanish in a mass extinction. And new genera can do the same thing again, multiple times. It is not a long voyage. It is an evolutionary epoch. The people who arrived at Andromeda after 25 million years of ship time would not be human. Not in any meaningful biological or cultural sense. Natural selection does not pause because you are on a spacecraft. With any mutation rate at all, over any significant fraction of a million generations, the population aboard the ship would change. Genetic drift in a small, isolated population, any population, would transform the gene pool beyond recognition in a fraction of that time. The genetic diversity of the founding population would be reshuffled, amplified, reduced by bottlenecks, and ultimately sent in directions impossible to predict. The radiation environment of deep space makes this worse. Outside the protective cocoon of a planetary magnetic field and thick atmosphere, cosmic rays and high-energy particles continuously bombard biological tissue. On the International Space Station, astronauts accumulate radiation doses at roughly 10 times the surface rate, and the station sits in low Earth orbit, still well within the magnetosphere. In true deep space, far from any star, the radiation environment is harsher still, and over millions of years, the cumulative DNA damage, even accounting for repair mechanisms, would drive mutation rates far above what any controlled breeding program could compensate for. And then, there is the question of social continuity. A civilization is not just its biology. It is its institutions, its languages, its shared memory, its purposes. Human cultures in total isolation have transformed beyond recognition in a few thousand years. The linguistic, technological and social distance between a settlement founded today and its descendants in 5,000 years is already enormous. As the gap between ancient Sumerian city-states and modern nation-states demonstrates. Over 25 million years, no cultural continuity of any recognizable kind could survive. The mission briefing locked in the ship's archive, explaining why the journey was started and what the founders hoped to find, would be as legible to the arrivals as a message from a species that no longer exists. Because that is exactly what it would be. The civilization that set out for Andromeda would be unrecognizable long before arrival. Or extinct. Those are the two realistic outcomes. Unrecognizable or extinct. And the people on the ship would have been born into a universe they could never leave, carrying out a mission whose original purpose had dissolved into mythology thousands of generations before their birth, moving through an emptiness so total and so ancient, it had outlasted every idea their ancestors ever formed. There is something deeply melancholy about that image, but also something that demands a harder question. One that physicists and philosophers have been quietly circling for decades. If the intergalactic distances are this absolute, if no civilization can cross them without being transformed beyond recognition or destroyed, then what does that mean for the universe as a whole? For the question of whether we are alone? For the strangest silence in all of science? The fact that after 60 years of listening, we have heard nothing. The answer to that silence might be written in the same mathematics we have just been working through. Our local group, our gravitational neighborhood, the roughly 80 galaxies held together against the pull of dark energy, might be far less of a limitation than it first appears. Because something is coming that reframes the entire question of what our neighborhood even means. Something vast, inevitable, and on cosmic timescales already well underway. 4 billion years from now, if anything on Earth still has eyes, the night sky will look wrong. Not dramatically wrong at first, not catastrophically, just wrong. The familiar scatter of stars will be the same, the constellations more or less intact. But low on the horizon, or perhaps filling a quarter of the sky depending on the season and the hemisphere, Andromeda will no longer be a faint smear, requiring dark skies and patience to detect. It will be a structure, a presence, a second galaxy, close enough to resolve individual star-forming regions with the naked eye, its spiral arms stretched across degrees of sky, its core glowing like a second, diffuse sun that never rises and never sets. Astronomers today have already simulated what this will look like in detail, using computer models that track the gravitational interactions of billions of stars across billions of years. The simulations agree on the broad strokes. Andromeda is currently approaching at roughly 110 kilometers per second. It has been falling toward us for most of the universe's history, and in approximately 4 to 5 billion years, an interval roughly equal to the current age of the Earth, the two galaxies will begin their first close pass. Notice what I said, first, because this is not a single collision in the way that word implies. Two galaxies interpenetrating is a slow-motion gravitational ballet that plays out over hundreds of millions of years. The first pass will distort both disks enormously, pulling long tidal tails of stars out into intergalactic space, warping the spiral structure of both galaxies into shapes that have no name in current astronomical vocabulary. Then the two systems will partially separate, slow, fall back together, interpenetrate again. The process of merging completely into a single, large, elliptical galaxy takes roughly 2 billion years from first contact. During all of this, the night sky above whatever planet might be watching, if any planet survives the gravitational reshuffling, if any life persists on it, will be the most spectacular in the history of any world in either galaxy. Not because stars will be colliding. They won't be. Not in any significant numbers. The distances between individual stars are so vast that even two entire galaxies passing through each other is mostly empty space moving through empty space. But the sky will blaze with new star formation, triggered by the compression of gas clouds as they collide and collapse. Star nurseries, lit up across both galaxies simultaneously. Nebulae on a scale that makes the Orion Nebula look like a match flame. The galactic center, which today is a smudge on a dark night far from city lights, will be a river of light, crossing the sky from edge to edge. Any civilization that exists to witness it will have a front row seat to the largest event in the history of the local group. And they will be powerless to do anything but watch. Not because of any failure of technology, but because on the scale of what is happening, any spacecraft, any signal, any act of agency is like a dust mote trying to redirect a hurricane. The merged galaxy, Milkomeda, as some astronomers have already started calling it in papers and public talks, will eventually settle into a roughly spherical distribution of stars. No longer a disk, no longer showing spiral structure, its gas largely consumed in the burst of star formation the merger triggered. It will be a different kind of object entirely. Quieter, older, an enormous elliptical galaxy containing the combined stellar populations of two great spiral galaxies, plus whatever dwarf galaxies had been absorbed along the way. And surrounding it, on all sides, will be nothing. Not metaphorical nothing, actual cosmological nothing. By the time Milkomeda has fully formed, somewhere in the range of 7 to 10 billion years from now, the rest of the universe will have retreated far beyond any possible contact. The nearest galaxy clusters outside the local group are already receding. The Virgo cluster, the nearest large cluster of galaxies beyond our own neighborhood, sits about 54 million light-years away. Right now, its light can reach us. Right now, in principle, in the most theoretical, energy-be-damned sense, a signal sent today could eventually get there. But dark energy is accelerating the expansion continuously, and within a few 100 billion years, every galaxy outside the local group will have crossed the cosmic event horizon for good. Think about what that means for any civilization that forms in that distant era. They will look out at the sky and see stars, their own galaxy, the merged remnant of what was once the Milky Way and Andromeda. And beyond the outermost stars of Milkomeda, darkness. Not the darkness we see between stars tonight, which is populated with faint smudges of other galaxies if you know where to look and have a good enough telescope. Real darkness. Cosmological darkness. A void with nothing in it, not because the other galaxies were destroyed, but because they receded so far and so fast that their light, stretched to infinite redshift by the expanding space between then and now, simply ceased to arrive. A civilization born in that era would have no way of knowing that 2 trillion other galaxies exist. They would have no fossil light, no ancient signal, no cosmological background radiation pattern pointing towards structure beyond their own neighborhood. They would look at the sky, map every star, build every telescope imaginable, and conclude, with complete logical consistency, that they live in a universe containing exactly one galaxy. Their galaxy. We know this only because we happen to live at the right moment, early enough in cosmic history that the evidence of the universe's full extent is still visible, still arriving, still detectable. The cosmological constant, the dark energy term that Einstein introduced into his equations in 1917, removed in shame when Hubble showed the universe was expanding, and then reinstated after the 1998 supernova observations, is essentially a timer, set the moment the universe began, counting down to a future in which intelligence, if it exists, will be profoundly and permanently deceived about the scale of its own cosmos. We got lucky. We exist at the exact moment when the universe is old enough to have formed stars, planets, and complex life, but not so old that all evidence of its true scale has vanished over the cosmic horizon. The window for knowing what the universe really is may be, in cosmic terms, quite brief. And we are living in it. Now hold that thought, the window, the timing, the extraordinary coincidence of existing when we do, and turn it toward the strangest unanswered question in all of science. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos, and the conversation turned to extraterrestrial intelligence. Fermi, by reputation, could cut through complexity to the core of a quantitative problem faster than almost anyone alive. He ran through the numbers quickly in his head: the age of the galaxy, the number of stars, the plausibility of planets, the time available for intelligence to evolve, and then asked, as simply as he might have asked the time, "But where is everybody?" The question, known since as the Fermi paradox, has never been answered. The galaxy is old enough and large enough and contains enough stars with enough planets that if intelligence arose anywhere else and developed technology on even a modest timescale, evidence of it should be visible, should have reached us by now, should, by some analyses, have had time to spread across the entire galaxy multiple times over. And yet, silence. 60 years of dedicated radio telescope observation, increasingly sensitive equipment, expanding search parameters, and nothing. No signal, no artifact, no megastructure, no pattern in the noise that could not be explained by natural processes. The isolation we have been describing, the physics of it, the mathematical absoluteness of it, may be part of the answer, and not in the comforting way. If the physics of intergalactic travel is as prohibitive as the numbers show, then no civilization from outside the local group could ever reach us, regardless of how advanced they became. The horizon cuts both ways. We cannot reach them, and they cannot reach us. The 2 trillion galaxies beyond our local neighborhood are not just unreachable destinations, they are unreachable sources. Whatever intelligence might exist in the Virgo cluster, in the Coma cluster, in the great filaments and walls of galaxy clusters stretching across the observable universe, it is permanently quarantined from us by the same dark energy that quarantines us from it. The universe is not full of civilizations we haven't heard from yet. It may be full of civilizations that are physically incapable of ever contacting each other. Not because they haven't developed the right technology, but because the universe's architecture makes contact geometrically impossible across intergalactic distances. Each local group, each gravitationally bound island in the expanding sea of space-time, may be its own completely isolated experiment in physics and chemistry and biology, running independently, in permanent ignorance of every other experiment running simultaneously elsewhere. If that is true, and the physics gives us serious reasons to consider it, then the Fermi paradox is not really a paradox at all. It is a description. The universe does not permit intergalactic communication. Intelligence, wherever it arises, is confined to its own cosmic neighborhood, sealed in by the expansion of space itself, looking out at a darkening sky and hearing exactly what we hear. Nothing, everywhere, forever. I find that genuinely difficult to sit with. Not frightening exactly, but heavy. The universe is not hostile to intelligence. It produced us, after all, and possibly others. But it built its largest structures at scales that make communication between them impossible. It allowed life to evolve, allowed minds to form, allowed telescopes and radio arrays and space missions and abstract mathematics, and then drew the walls of the prison so far out that it took us until 1998 to notice they were there at all. But here is where I want to push back against the word prison, because a prison implies a punishment, an enclosure imposed from outside on something that would otherwise be free. And the Milky Way, our galaxy, our local group, our gravitational neighborhood, is not that. It is something closer to the opposite. The Milky Way contains somewhere between 100 and 400 billion stars. The latest estimates lean toward the higher end. 400 billion stars, each one a nuclear furnace running on physics that was set at the Big Bang. Among those stars, the current best estimates suggest the majority host planetary systems. The number of planets in our galaxy alone is thought to exceed 1 trillion. 1 trillion worlds, orbiting 400 billion suns in a structure 100,000 light-years across, which we have been exploring, physically, with instruments, with our bodies, for exactly 66 years since Yuri Gagarin first left the surface. 66 years. Against 100,000 light-years. Against 400 billion stars. Against 1 trillion worlds. We have barely exhaled. The Milky Way contains more unexplored territory than any civilization could meaningfully survey in 1 billion years of dedicated effort. It contains star-forming regions where new suns are igniting right now. Stellar nurseries like the Carina Nebula and the Eagle Nebula, where the gas and dust are collapsing under gravity and beginning the process that ends with planets. It contains the ruins of dead stars, white dwarfs cooling over billions of years, neutron stars spinning hundreds of times per second, black holes of stellar mass, and supermassive black holes anchoring the rotation of the galaxy itself. At the center, Sagittarius A star, a black hole 4 million times the mass of the Sun, sits in relative quiet now, but carries the record of violent activity in its surrounding stars, orbiting in ellipses that took decades of patient infrared observation to map. Andrea Ghez spent 27 years, from 1995 to the Nobel Prize she received in 2020, tracking the motions of individual stars within a fraction of a light-year of Sagittarius A star. One star in particular, called S2, completes a full orbit around the galactic center in just under 16 years, moving at roughly 3% of the speed of light at its closest approach. Ghez and her collaborators at UCLA built new adaptive optics systems, developed new analysis techniques, negotiated decades of telescope time, and produced the most precise observations of a black hole's gravitational influence ever made. The data confirmed general relativity in the most extreme gravitational environment we can directly observe. It mapped the mass of the central black hole with extraordinary precision. And it produced images of individual stars orbiting something invisible, something of inconceivable density, something that bends space-time so severely that starlight curves around it. Located in the heart of our own galaxy, 26,000 light-years from Earth. 26,000 light-years is not an abstract cosmological distance. By the standards of the universe, it is our backyard. We can see it with infrared telescopes. We can track individual stars near it. We have been watching them orbit for 3 decades with instruments mounted on a volcano in Hawaii. Our galaxy contains wonders we have not finished describing, structures we are still discovering, physics we are still working out, at a level of observational access that would not be available from any other galaxy. There is one more thought I keep returning to, and I want to leave it with you. The light you see when you step outside on a clear night and look up, the light from the stars, left those stars years ago. Decades, centuries for some of them. The light from the center of the Milky Way left 26,000 years ago, when our ancestors were painting animals on cave walls in southern France. The light from Andromeda, that faint smear in Perseus, visible on a dark autumn night, has been traveling for 2.5 million years. It predates our genus entirely. It left Andromeda before Homo habilis first chipped a stone. Every time you look up, you are looking back. Not metaphorically, literally. The night sky is a time machine, pointed in every direction simultaneously. And every photon that reaches your eye has been traveling for longer than most things you can name. The universe is presenting its history to you, continuously, for free, from a fixed position in the suburbs of a spiral galaxy, in a gravitationally bound cluster, in one small corner of an expanding cosmos. We are not going to leave. The physics is absolute on this point. The distances are real. The energy requirements are prohibitive. The expansion is accelerating. The horizon is closing. No engine we can conceive will change this. No breakthrough in propulsion will make Andromeda reachable in a human lifetime without time-dilating the traveler into a being with no connection to the world they left. The Milky Way is, in every meaningful sense, our permanent home. But permanent home is not the same thing as small home. 100,000 light-years, 400 billion stars, 1 trillion planets by current estimates. Physics that we have been studying seriously for roughly 300 years and still cannot fully explain. Dark energy, dark matter, the quantum behavior of space-time at the Planck scale, the information paradox at the boundary of black holes. Questions that our best physicists spend entire careers on and still cannot close. Open problems that may require new mathematics we have not invented, new concepts we cannot currently form, new observations from instruments that do not yet exist. The wall around the Milky Way is real, but the Milky Way inside the wall is incomprehensibly large. There is a line attributed to the naturalist and writer Lauren Isley about looking up at the night sky and feeling simultaneously infinitely small and absolutely necessary. I think about that when I consider what it means to be permanently confined to one galaxy out of 2 trillion. It sounds like diminishment. It sounds like limitation. It sounds like the universe looked at everything it made and then locked us in one room of a mansion we can never leave. But then I remember that the room has 400 billion lights in it, and most of them have never been visited. And some of them might be looked at by other eyes, from surfaces we have never mapped, by minds shaped by billions of years of evolution we cannot trace. And all of those lights, ours and theirs, if they exist, are held together by the same invisible force, the same gravitational web that kept dark energy from pulling us apart before we had a chance to exist. We are not prisoners of the Milky Way. We are residents of it. And the lease, barring catastrophe, runs for several billion years yet. On the clearest night you will ever see, somewhere far from city lights, somewhere the atmosphere is steady and the sky is fully dark, look up and find Andromeda. You will need to know where to look. It is faint, a smear rather than a point, located in the constellation Andromeda, northeast of the Great Square of Pegasus. Binoculars help. A dark-adapted eye helps more. When you find it, hold your gaze there for a moment. What you are looking at is the most distant thing you will ever see with your naked eyes. Every photon hitting your retina from that direction has been traveling since before our species walked upright. And that galaxy, that island universe that dismantled the comfortable cosmos when Hubble found a blinking star inside it in 1923, is moving toward you. Slowly by human standards, but surely, drawn by the same gravity that holds every planet in its orbit and every star in the galaxy's arms. In 4 billion years, it will fill the sky. You will not see that. Neither will I. Neither will anything that currently lives. But the light is already traveling. The galaxies are already moving. The merger has already been set in motion by the same initial conditions that produced the Big Bang, the first stars, the heavy elements, the sun, the Earth, and the particular configuration of chemistry and luck that resulted in a species capable of looking up and asking why it can never leave. That question, why we are here, contained, unable to cross the void, is not a tragedy. It is the question, the most honest question our situation generates. And the fact that we can ask it, from a rock orbiting an unremarkable star in the suburbs of a spiral galaxy that is one of 2 trillion, means that the universe produced something capable of understanding its own architecture. That is not nothing. That might be everything. If this kind of question is the kind that keeps you looking up, subscribe and keep watching. Because the universe is not finished surprising us. Not even close.